We know that magnetic force magnetic field exerts a magnetic force on charged particle, and similarly, the same phenomena happens when electric motor work. How it happens? The forces that make it turn are forces that a magnetic field exerts on a conductor carrying a current. So the magnetic forces on the moving charges within the conductor are transmitted to the material of the conductor, and the conductor as a whole experiences a force distributed along its length. Uh, so we can compute the force on a current carrying conductor starting from the magnetic force, which is F is equal to Q cross B, and on a single moving charge. So here is a straight segment of a conducting wire with length L and cross-sectional area A. The current is from bottom to top. The wire is in a uniform magnetic field perpendicular to the plane of the diagram and directed into the plane. So, and for simplicity, let's assume the moving charges are positive. If the moving charges is positive, then the drift velocity is upward and it is perpendicular to magnetic field. The average force on each charge would be and here the average so the average force here is directed towards left side. Since this VD and B are perpendicular, the magnitude of the force is given by F is equal to QBD. So now we will find the total force on all the moving charges in a length L of the conductor with cross-sectional area A. So the number of charges per unit volume is N. We are going to do the same thing which we did in last chapter when we find out the drift velocity and current density. So the number of charges per unit volume is N. A segment of conductor with length L has volume AL and contains a number of charges equal to NAN. So the total force on all the moving charges would be F. And this is so the current we know current density is equal to N Q into VT, and the product of current density into area is equal to total current. So this equation can be modified into force I. This becomes J turns to I, L and D. Okay. Now if the field is not perpendicular to the wire and makes an angle phi with it, so what we will do this in this situation, like here, then in this situation only the component of B perpendicular to the wire will be used, it will exert a force. and this is B perpendicular B sine phi. The magnetic force on the y segment then become, so the force is always perpendicular to both the conductor and the field, and with the direction determined by the same right hand rule we use for a moving positive charge. So hence this force can be expressed as a vector product just like the force on a single moving charge. So we represent the segment of wire with a vector L along the wire in the direction of the current. Then the force on this segment becomes, this is magnetic force on a straight wire segment. And here there are two different cases. If the magnetic field length L and force vectors, this one here is, there is a simple case, are perpendicular. Here we reverses the direction of the magnetic field. When we reverse the direction of the magnetic field, the direction of the force also reverses. Then if we reverse the direction of the current here, then the direction of the force again reverse back. So now if the conductor is not straight, we can divide it into small segments, dl, and then the force df will be calculated on each segment. Then this equation becomes, and we can integrate this one along the wire to find the total force on the conductor of any shape. And this integral is, if you remember from previous lectures, is called as line integral. Okay, now what happen, one more point is what happen if the charges are negative, like the electrons in a metal. Then this upward currents corresponds to a downward drift velocity, because q is now negative, the direction of force, but the direction of force remains the same. And these equations are valid for both signs of charges, negative and positive. And a common application of the magnetic forces on a current carrying wire is found in loudspeakers.